Hey everyone, and welcome back for another deep dive. Today, we're going to be tackling titration curves.
Ooh, fun.
Yeah, they're pretty cool.
Yeah.
You know those graphs that chart the course of a titration?
Yeah.
And we've got a whole bunch of articles and research here.
Cool.
I'm really excited to kind of unravel the secrets that these curves hold,
Yeah.
especially how they're used in real-world scenarios.
Yeah. You know what's fascinating about titration curves is that they go beyond just the basic what of a reaction,
Mm,
and they reveal the why behind the changing pH.
right.
It's like having a window into the dynamics of the solution.
Okay, so let's jump right in.
Mm-hmm.
I was playing around with this interactive titration curve generator
Uh-huh.
from one of the sources,
Yeah.
and it really hit me how much the type of acid and base you use can really shake things up.
Right.
Like a strong acid-strong base titration has a totally different curve than a weak acid-strong base one.
Absolutely. And that difference really boils down to the degree of dissociation.
Right.
A strong acid completely breaks apart in solution. Yeah.
So you get a rapid pH change during neutralization,
Mm-hmm.
but with a weak acid, it's a much more gradual process,
Okay.
which is reflected in the curve's gentler slope.
So if I'm looking at a titration curve, one of the first things I should try to figure out is whether I'm dealing with a strong or weak acid.
Exactly.
That'll give me a head start in interpreting the rest of the curve, right?
Exactly. It's like figuring out the personality of the reaction
Right.
before diving into the details.
Yeah.
Now, you mentioned that interactive generator.
Yeah.
Did you notice how changing the concentration of the solutions affects the curve?
Yeah, I did. It seemed like increasing the concentration made the curve steeper.
Okay.
Is that because you're adding more moles of acid or base per drop,
Uh-huh.
leading to faster changes in pH?
You nailed it. It's all about the rate of change.
Okay.
Higher concentrations mean more dramatic shifts in pH
Yeah.
as you titrate.
That makes total sense.
Cool.
No, I remember from chemistry class that the equivalence point is a big deal in titration curves.
Right. It's where the moles of acid and base are perfectly balanced.
Right, but it's more than just a balancing act.
Okay.
The pH at the equivalence point tells us something crucial about the solution.
Okay.
For a strong acid-strong base titration, it's neutral pH 7.
Yep.
But things get more interesting with weak acids and bases.
Yeah, like if you're titrating a weak acid with a strong base, the equivalence point isn't at pH 7.
Right.
Why is that?
It does. It all comes down to the salt formed during neutralization.
Okay.
With a weak acid and strong base, that salt is basic.
Uh-huh.
So the pH at the equivalence point ends up higher than 7.
So you're telling me the salt itself can influence the pH?
It is. And it highlights why understanding the chemical species present at each stage of the titration is so important.
Right.
We're not just dealing with reactants and products.
Right.
We have to consider the ions they form and how they interact with water.
Okay, I'm starting to see how titration curves are like mini dramas unfolding in the beaker. We've got characters, plot twists, and a resolution at the equivalence point.
Right.
But there's one more character I remember encountering in the sources.
Okay.
The pKi.
Ah, the pKi.
How does that fit into this story?
It's not just a number. It's a key to unlocking the acid's strength and its buffering capacity.
Right.
Remember, the lower the pKi, the stronger the acid.
So a strong acid would have a pKi close to 0,
Uh-huh.
while a weak acid might have a pKi of, say, 4 or 5.
Precisely. Now, here's where the pKi gets really interesting.
Okay.
When the pH of the solution equals the pKi of the weak acid, we hit a sweet spot.
A sweet spot. Tell me more. What makes it so special?
At that pH, we have equal amounts of the weak acid and its conjugate base in the solution.
Okay.
It's like a perfectly balanced team ready to tackle any pH disturbances.
Right.
And that, my friend, is the essence of a buffer solution.
Hold on, buffers. Those are the chemical superheroes that resist changes in pH, right?
Yes.
But I don't get how they're connected to the pKi.
Yeah.
They're from different comic book universes.
Think of it this way. The pKa is like the origin story for a buffer.
Okay.
When the pH equals the pKa,
Uh-huh.
you create the perfect conditions for a buffer to emerge and do its job,
Mm-hmm.
maintaining a stable pH.
Okay. That's starting to click.
Good.
So when we're looking at a weak, acid-strong base titration curve,
Mm-hmm.
that point where pH equals pKa is like the buffer's headquarters.
You got it. And
Yeah.
that's why that point on the curve often corresponds to the maximum buffering capacity of the solution.
I'm already feeling like a titration curve detective piecing together clues.
Good.
We've got the type of acid and base the equivalence point to the pKa and now buffer solutions.
Yeah.
It's like a whole interconnected web of concepts.
And we've only just scratched the surface. There's so much more to uncover as we delve into specific types of titration curves and their real-world applications.
Well, I'm ready to keep digging. Let's pick a specific titration scenario and really dissect it step by step.
Sounds good.
How about we tackle a strong, acid-strong base titration first? That seems like a good foundation to build on.
Excellent choice. Strong, acid-strong base titrations are like the classic superhero story.
Okay.
Straightforward and action-packed. Let's jump in.
All right, so imagine we have a beaker with a strong acid, like hydrochloric acid,
Oh, yeah.
HCl,
HCl.
and we're slowly adding a strong base like sodium hydroxide, NaOH drop by drop.
Okay, I'm picturing it. I've got my virtual lab coat on,
Right.
my imaginary burette ready to go.
Perfect. Now, before we even add a single drop of the base,
Okay.
what's the pH of the solution going to be?
Well, we've only got the strong acid in there.
Yeah.
And strong acids are like the pH rock stars that
Yeah.
completely dissociate.
Uh-huh.
So the pH is going to be pretty low, right?
Exactly. It'll depend on the concentration of the HCl,
Right.
but it's going to be strongly acidic, somewhere down in the low pH range.
Okay. So we're starting off our titration curve with a low pH.
Yeah.
Now, as we start adding the NaOH, what's happening at the molecular level?
Okay.
It's like a chemical battle is about to begin.
Yeah.
You got it. The AOH is coming in with its hydroxide ions,
Uh-huh.
OH,
Okay.
ready to neutralize those acidic hydrogen ions, H plus from the HCl.
Right.
It's a classic acid-base reaction.
Yeah.
H plus and OH combine to form water, H2O.
So the pH starts to rise as those H plus ions get neutralized.
Exactly.
But since we're dealing with a strong base,
Yeah.
I bet that pH climb is pretty steep, right?
You're catching on quickly. The strong base readily releases those OH ions.
Okay.
So the neutralization happens rapidly, resulting in a sharp increase in pH. That's what gives the strong acid-strong base titration curve its characteristic steep slope in the middle.
Okay, so we've got the initial low pH.
Right.
The steep climb as we add the base.
Yeah.
And then we hit that crucial point, the equivalence point.
Okay.
What's the scene at the molecular level when we reach that point?
At the equivalence point, we've added just the right amount of NaOH to completely neutralize all the HCl. Every H plus ion has found its OH partner, and they've all happily combined to form water.
So it's like a perfectly balanced chemical equation.
Precisely.
No leftover acid or base, just a solution of water and the salt formed during the reaction.
Exactly. And in this case, since we started with a strong acid and a strong base,
Right.
that salt is neutral.
Okay.
It doesn't affect the pH of this solution.
That's why the equivalence point for a strong acid-strong base titration is always at pH 7,
Right.
neutral territory.
It's like the calm after the chemical storm.
Right.
But now let's imagine we switch things up.
Okay.
Instead of hydrochloric acid, let's say we start with a weak acid.
Okay.
Like acetic acid,
Uh-huh.
CH3COOH.
Okay.
The stuff that gives vinegar its tang.
Right.
How do you think that's going to change our titration curve adventure?
Ooh, this is where things get interesting. Weak acids are a bit more reluctant to give up their H plus ions.
Yes.
Right?
Yes.
So I'm guessing the pH won't change as dramatically at the beginning?
You're on the right track. Remember, weak acids only partially dissociate.
Right.
So we have a mixture of the undissociated acid molecules
Okay.
and those H plus ions floating around.
So when we start adding the NaOH, those OH ions will still go after the H plus ions, but there's not going to be a sudden surge in pH.
Right.
Because the weak acid is holding on to some of its H plus reserves.
Exactly. The pH will rise, but more gradually.
Okay.
That's why the initial part of the curve for a weak acid-strong base titration has a gentler slope compared to the strong acid-strong base scenario.
And what about the equivalence point? Is it still at pH 7? Something tells me things might be a little different here.
You've got a good intuition. Remember that salt we talked about?
Yeah.
The one formed during neutralization?
Right.
With a weak acid and a strong base, that salt isn't neutral anymore.
Wait, so the salt can actually tip the pH scales?
Yeah.
It's not just a spectator in the reaction.
Not this time. In this case, the salt formed is basic. And it's going to have a say in the pH at the equivalence point.
Okay.
So instead of ending up at pH 7, we'll see the equivalence point shifted to a higher pH,
Okay.
making the solution slightly basic.
Wow, so even though we've neutralized all the acid,
It is.
the solution isn't actually neutral. That's a bit counterintuitive.
It is. But it makes perfect sense when you consider the interplay of all the chemical species involved.
Right.
It's a reminder that titration curves are more than just lines on a graph. They're stories about the dynamic relationships between molecules and ions in solution.
And let's not forget about our buffer friend.
Right.
I'm guessing that special point where pH equals pKa is going to play a role in the weak acid-strong base titration too.
Absolutely. Remember, that's the point where we have that perfect balance of the weak acid and its conjugate base,
Right.
creating our buffer superhero team.
Yeah.
And in a weak acid-strong base titration, that buffer region shows up before the equivalence point.
So as we're adding the NaOH, there's a zone on the curve where the pH changes very little because the buffer's working its magic, resisting those pH shifts.
Exactly. It's like a plateau on the curve, a testament to the buffer's power to maintain stability. And the closer we get to that pH equals pKa point, the stronger the buffer's defense becomes.
Okay. I'm starting to see the bigger picture here.
Yeah.
Strong acid-strong base titrations are like straightforward battles, while weak acid-strong base titrations are more like strategic games.
Right.
With buffers and salts adding layers of complexity.
That's a great analogy. And the more we understand these different titration scenarios, the better equipped we are to analyze and interpret real-world titration curves.
This is making me think of all the practical applications of titration.
Yeah.
It's not just a lab technique, it's used in so many different fields.
Absolutely. For example, in medicine, titration is crucial for determining the correct dosage of medications.
Oh, right.
Too much or too little of a drug can have significant consequences. So precise titration is essential.
And I bet it's used in environmental science too, right?
Yes.
Like for monitoring water quality or soil pH.
You're right on target. Titration is a fundamental tool for environmental scientists to assess the health of ecosystems and track changes over time.
It's amazing how this seemingly simple technique of adding one solution to another has such a wide reach.
It is. And it all comes back to those titration curves.
Right.
By understanding the shapes of these curves and the chemical stories they tell, we gain insights that extend far beyond the lab bench.
This deep dive has definitely broadened my perspective on titration.
Good.
It's not just about memorizing equations, it's about unraveling the intricate dance of molecules and ions in solution.
And that dance can reveal so much about the world around us, from the pH of our blood to the health of our planet.
So before we wrap up, I want to challenge our listeners with a final thought experiment.
Okay.
Imagine you're presented with a titration curve. But you have no information about the acid or base involved. What clues would you look for in the curve to try to figure out what type of titration you're dealing with?
Ooh, that's a great challenge. What are your thoughts?
Well, I definitely pay attention to the initial pH.
Okay.
Is it strongly acidic, suggesting a strong acid? Or is it a bit higher, hinting at a weak acid?
Excellent point. And what about the shape of the curve?
Right.
Is the pH change steep and sudden or more gradual and subtle?
Right. That could tell us whether we're dealing with a strong or weak base.
Exactly.
And then, of course, I'd focus on the equivalence point.
Okay.
Is it a pH 7 or is it shifted to a higher or lower pH, suggesting the presence of a basic or acidic salt?
Those are all great observations. By carefully analyzing the shape, slope, and key points on the curve, you can start to piece together the identity of the acid and base like a true titration detective.
This has been a fascinating journey into the world of titration curves. It feels like we've gone from peering through a foggy window to having a high-definition view of what's happening during titrations.
It's like we've upgraded our chemistry goggles, right?
Exactly. And now I can't help but notice titration curves everywhere.
Yeah.
Like the other day I was baking bread, and I realized the process of adding yeast to the dough and watching it rise is kind of like a titration.
That's a great connection. You're essentially controlling the pH of the dough by adding the yeast,
Right.
which produces carbon dioxide and acidifies the environment.
Okay.
It's a subtle titration happening right in your kitchen.
I never thought about it that way. It's like chemistry is secretly running the show in so many aspects of our lives.
It really is. And the more we understand these underlying chemical principles, the more we appreciate the intricate web of interactions that make up our world.
Okay, before we get too philosophical, I want to circle back to something we touched on earlier.
Okay.
The pKa value.
Right.
You mentioned it's related to an acid's strength.
Yeah.
But I'm still a bit fuzzy in the details. Can you break it down for me?
Absolutely. So remember that acids donate protons H+ in solution. The pK value essentially tells us how willing an acid is to give up that proton.
Okay.
It's a measure of its acidity.
So a lower pK means a stronger acid,
Uh-huh.
one that's eager to donate its proton.
Exactly. Think of it like this. A strong acid is like a generous friend who readily shares their snacks.
Okay.
A weak acid, on the other hand, is a bit more hesitant to part with its proton like someone guarding their favorite treat.
That's a funny analogy.
Yeah.
So hydrochloric acid, our strong acid friend, has a very low pKa,
Right.
while acetic acid, our weak acid buddy, has a higher pKa.
Exactly. And knowing the pKi of an acid can be incredibly useful.
Okay.
It helps us predict how it will behave in different situations,
Right.
especially when it comes to buffer solutions.
Ah, buffers. They're like the pH superheroes, always there to maintain balance.
Yes.
But I'm still trying to wrap my head around their connection to the pKa.
Okay.
It's like they're speaking different chemical languages.
Think of the pKi as the buffer's secret code. It tells us at what pH the buffer will be most effective. It's optimal operating zone, if you will.
Okay, so when the pH of the solution matches the pKa of the weak acid, we have that ideal buffer situation.
You got it. It's like having a perfectly balanced team ready to defend against any pH disturbances.
This is making me realize how much information is packed into a single titration curve.
Yeah.
It's like a treasure map that once you know how to read it, reveals all sorts of secrets about the solution.
And the best part is these secrets aren't just confined to the lab. They have real-world implications in fields like medicine, environmental science, and even food production.
It's like learning a new language that allows us to understand the world in a deeper way.
Exactly. And just like with any language, the more we practice, the more fluent we become.
Yeah.
So keep exploring those titration curves, keep asking questions, and keep those chemistry goggles polished.
Well, on that note, I think it's time to wrap up our deep dive. Thanks for joining us on this exploration of titration curves. We hope you've gained some new insights and maybe even a newfound appreciation for the elegant dance of molecules in solution.
It's been a pleasure diving into this topic with you. Until next time, keep those minds curious